we're going to write this as, now I did some manipulation here. You know that any quantity raised to the power of 0 is 1. So, since there is no term on the left side using L, I wrote this quantity T as L to the power of 0, T to the power of 1. Did you understand that? Well, I don't need to write L to the power of 0. L to the power of 0 is simply 1. I can as well write it as Z to the power of 0, because anything to the power of 0 is 1. Now, why did I do that? Because I see an L on the right side, so on the left I introduced an L. L to the power of 0. T to the power of 1 equal to K, look at this, L to the power of X times L to the power of Y is L to the power of X plus Y. Okay, what do you do next? We have an equation with a left side and a right side. And everything about the left side must be equal to the right side. Is that right? That's the meaning of an equation. So, if there is an L on the left side, the exponent of that L must be equal to the exponent of L on the right side. So we are going to do, equate the exponents of the same base on either side. What does that mean? It means 0 is the same as X plus Y. So, and 1 is the same as negative 2Y. The exponent of L on the left side must be equal to the exponent of L on the right side. I'm sure you agree with me there. The exponent of T on the left side must be equal to the exponent of T on the right side. So, I start by saying 1 equal to negative 2Y, and that gives me the value of Y. Y equal to negative 1/2. Now, also equating the powers of L, we have X plus Y equal to 0. What does that mean? It means X equal to negative Y. X equal to negative Y, but Y equal to negative 1/2. Therefore, X must be positive 1/2. See, look at the way we have been able to obtain the values of X and Y. And therefore, what is the equation for the period of a pendulum? We go back to this equation, replace X by 1/2 and Y by negative 1/2. So, this is the equation of the pendulum now. T, the period, equal to a constant K times L to the power of 1/2, A to the power of negative 1/2. I'm sure you know that a power 1/2 means a square root. So L to the power of 1/2 is square root of L. And what is A to the power of negative 1/2? It is 1 over A to the power of 1/2, which is 1 over square root of A. So how do you now write this in a more civilized way? That will be T equal to K times square root of L over A. And this is T, the period of the pendulum, is a constant times square root of length divided by acceleration caused by gravity. That's a beautiful equation. And you see how simply we were able to obtain it by using the method of dimensions. In physics too, we will obtain this equation using the oscillations of a pendulum. Okay. Let's now talk about significant figures. It is very important that we use numbers in their correct form. You see, every physical measurement involves a level of accuracy dictated by the instrument you use for measuring. For example, what is the accuracy of this meter rule? The smallest division that is marked on the meter rule is 1 millimeter. You cannot measure a distance less than 1 millimeter using this ruler. So the accuracy of this ruler is limited to 1 millimeter. Now, the accuracy of measurements is very often represented by using significant figures or significant digits, and you must be familiar with how to use significant digits. Measurements always involves a level of uncertainty, and we use significant figures to deal with this uncertainty. Significant figures are determined using some rules, and let's look at some of these rules. 1. Zeros at the beginning of a number are not significant. For example, 0.00257 has only 3 significant digits. What are they? 2, 5, and 7. The first 3 zeros are not significant in that measure. Rule number 2. Zeros within a number are significant. For example, 20.06. How many significant digits are there? It has 4 significant digits. That means 1, 2, 3, 4. Both these zeros are significant. Rule number 3. Zeros at the end of a number after the decimal point are significant. For example, 5.0. Now, the number 5.0 indicates that you are making measurement correct to 1 decimal place. That is a level of accuracy dictated by this. That 0 is significant. So, zeros after the decimal at the end of a number are significant. Now, 5.0 times 10 to the power of 2 has 2 significant figures, while 5.00 times 10 to the 2 has how many significant figures? Has 3 significant figures. That means in this measure, we expect an accuracy of 1/10. In a measure like this, we expect an accuracy of 100. So this is a much more accurate measure than this. Okay. When you report a final result, how many significant digits should there be? The final result of an operation should contain the same number of significant digits as the quantity with the least number of significant figures that was used in a calculation. Now, let's illustrate that with an example. The base of a triangle is 7.2 centimeter and its altitude is 4.35 centimeter. Find its area. Alright, what is the area of a triangle? If you notice, 7.2 has 2 significant figures, 4.35 has 3 significant figures. Tell me, using this rule, how many significant figures should there be in the answer? What does the rule say? The final result of an operation should contain the same number of significant figures as the quantity with the least number of significant figures that were used in the calculation. So we are using two numbers for our calculation. One has two significant figures, the other has three significant figures. Therefore, our answer must have two significant figures. Alright? If B is the base and H is the height of a triangle, then the area of the triangle is given by A equal to 1/2 of BH. Well, we know the base, we know the height, so that will be 1/2, 7.2 centimeter times 4.35 centimeter. We should write those units there, which is 16 centimeters squared. You can see I wrote the answer using two significant digits, and that is what I expect you to do also. Okay, now this has been a summary of measurement, units, significant figures, dimensions, and so on. If you take a lab with me, I will elaborate on this in the first lab. In fact, the first lab is the use of units and conversions, so that you get to know this in a little more detail. Alright? You need to go through that and make sure you understand these concepts very well. I'm going to stop this here. I'm going to continue with lesson 1.1 as a second part. I'm going to call it lesson 1.1b. I will be doing that throughout this course. In my lectures, I will divide each lesson into smaller units so that you don't have to watch a lesson for a long period of time. And in our next part, we will be starting our discussion on moving objects. And all these concepts we discussed, we will be using in there. Alright, I will see you for that lesson a little later.